Good morning, friends. In the last class, we are observing for exponential functions of this kind. The sampled version was fn e to the power alpha t to the power n. So, this we took as a constant c, and if alpha is positive, we observed e to the power alpha t is greater than 1, that is c is greater than 1. So, the response was the function fn was something like this. Okay. Thank you. This is for c negative, c less than 1, c less than 1, that is alpha negative. Okay. It was like this, and for c greater than 1, it was increasing like this. Okay. If c is less than 0, c is negative, then c to the power n is some negative quantity, all right, to the power n. Depending on the magnitude of that quantity, it may be decreasing in magnitude or increasing in magnitude, but it will be appearing alternately with alternate signs. One of our friends had asked, when do you get c negative? For alpha positive values or negative values, you do not get c negative, is it not? C was less than 1 or greater than 1, but when do you get c negative? Okay. Thank you very much. It is for a complex function. Suppose we have there is alpha equal to a plus j b, all right. A can be negative or positive, depending on that it will be exponentially increasing or decreasing. Let us select the sampling time such that b into t is say pi. We select the sampling time t such that the product of t and the frequency term b is equal to pi. Then what happens? E to the power alpha t, if I take the sampled values, will be e to the power a t to the power n e to the power j b t to the power n. Okay. So, this is some magnitude c to the power n, e to the power j b t, and b t is pi. Therefore, this is e to the power j pi to the power n. And what is e to the power j pi? Minus 1. So, minus 1 to the power n magnitude c to the power n. Is that all right? So, it will be c, depending on the magnitude of c, if it is greater than 1, then it will be more, it will start from 1, then c, then c squared, and so on. Okay. Now, suppose we have a function Fn say this is 1 0 minus 1 by 4 0 then 1 by 16. These are not shown to the scale. So, I am just writing the values on this. It is gradually diminishing in magnitude 1 by 64 and so on, and they are coming alternately plus minus with zeros appearing in between. Okay. So, it is 1 0 minus 1 by 4 0 1 by 16 and so on. What will be the representation of such a function? Could someone suggest? Pi by 2. Okay. So, c to the power n e to the power j pi by 2. Let us try e to the power j pi by 2 n. You mean this? Okay, let us see. C to the power n will take care of the magnitude part. Let us see e to the power j pi by 2 n what it gives. E to the power j pi by 2 n, what are the values for different values of n? N is equal to 0, it is 1, n is equal to 1, e to the power j pi by 2. So, that will be j, and then minus 1, then again minus j, then plus 1, then j and so on. Okay. So, that does not satisfy this. I have to have another term, which I can write. I will complement these j's if I add them together and then take the average, I will get. So, I call this as some y1 series and y2 series. So, y1 plus y2 by 2 will give me the desired series. Okay. So, it will not be e to the power j pi by 2 n alone, it will be and average of this. Is that all right? Could it be 1 to the power n and minus 1 to the power n? Instead of pi, if I take 1 to the power n and minus 1 to the power n. So, basically this is half of c to the power n, this is j. So, j to the power n plus minus j to the power n. Is that all right? This is j to the power n plus minus j to the power n, half of that. Now, my next question is, could it have been 1 to the power n and minus 1 to the power n? Let us see. Half of this, what does it give me? 1, and then if I put n is equal to 0, n is equal to 0, 1, n is equal to 1, n is equal to 2, again 0, again 1. So, this will give me a series 1, 0, 1, 0, 1, 0 and so on. So far as this term is concerned, equivalent of this term, that gets multiplied by c to the power n. So, it will be modulated. So, it will be either exponentially decreasing or increasing, but the terms that will be appearing will be alternately coming with positive signs, and in between there will be zeros. So, if you have signals of this kind, where c is less than 1, it will be decreasing, and if there are zeros in between, it will be like this. Okay. We will get back to this kind of exercise again later on. Now, x n, the series, is normally written, if it is a finite series, then say -2, 3, 0, -1, 2, 5, 1, and this is a finite series. I show by an arrow, suppose there is an arrow here, that means this is the origin. So, this is in the negative region of time, this is in the positive region of time, that is the sequence is defined both in negative and positive directions. So, this is at this point it is -1, 2, 5, they are not to the scale, 1, 0. If it is terminated here, that means hereafter these are all zeros, 0, then 3, -2, and so on, rest are all zeros. So, by showing an arrow here, you show the location of the origin. Okay. This is the origin. The sequence x n may be defined over a range it is a finite range where m1 is greater than -infinity and m2 is less than +infinity. That means, between some m1 which may be in the negative region of time and some m2, it is defined, all right, like the previous one. Here this is 0, -1, -2, -3. So, m1 was up to -3, m2 was up to +3. So, what is the sequence length? What will be the sequence length? One, 2, 3, 4, 5, 6, 7, all right. So, 3 plus 3 minus of -3 plus 1. Okay. So, m2 minus m1 plus 1, this will be the length of the sequence. Okay. m1 could have been here also, then also m2 minus m1 would have been this much. Like in the continuous domain, we also define here in the discrete systems even and odd functions. Or even and odd sequences. So, any sequence x n if it is an even sequence, then it will be same as x minus n. So, this is the condition for even sequence. Such sequences we shall write as x e n, x even n. Similarly, an odd sequence will follow this relationship and we will denote these as x o n. Okay. any sequence x n can be written as a sum of an even component and an odd component. Okay. Now, how do you find out the even component? You take x n plus x of minus n divided by 2, that gives you x e n. Okay. Similarly, x n minus of x of minus n divided by 2 will give you x o n. Let us take an example. We are given x n as say 2 minus 1 1 0 3. What will be the even sequence? Could someone tell me? What are the values in the negative region of time? All zeros. If I have the origin here, okay, on this side of this arrow, left side it is all 0. So, it will be half of this sequence plus its negative region values divided by 2. So, it will be half of all the values. Should it be half? Any disagreement? First one, so it will be 2. Then minus half, then half, then 0, then 1.5. Is that okay? So, I have a sequence graphically. If we show, if this is 2 minus 1 1 0 and 3, its corresponding even part, this is x n. This is n, okay. All right, there is a break here. Then the even part will be 2, then it is minus half, then plus half, then 0, then 1.5. So, except the first value, others are all halved. The first value is remaining as it is, all right, because when you add with this, x minus 0 is also same as x plus 0. So, that divided by 2 means the original value. So, all other values will be reduced to half. What will be the odd sequence? Okay, let us see. X odd, it will be 2 minus 2, 0, then this one will be same. So, minus 0.5 plus 0.5, 0, 1.5. So, the odd sequence will be 0, minus 0.5 plus 0.5, 0 and 1.5. Okay. See, except for the first value, others are same. So, you mean to say except the first value, an even function and odd function will appear identical? So, where is the difference? So, even function is, though we are showing it only in the positive region of time, it is also having its counterpart in the negative region which has not been shown. So, the total function is a mirror image of this plus this itself. Okay. So, x n, if you take a mirror image on this side and then club with this, that will be the even part x e n. Similarly, if I take a mirror image of this twice, once about y axis, then again about x axis. So, I will get its replica on this side. So, first quadrant and third quadrant symmetry. So, it will be, for example, the odd function, if we take x o n, the total function will be 0.5 minus 0.5, 0 and minus 1.5. Okay. Sorry. So, this is the total function. Normally, we do not show this part, it is understood it will be having these values. In the negative region, it will have just negative of these values. Similarly, the even part, we do not show the left hand side, but it is also having these values. So, even function and odd function will be maybe much longer in sequence compared to the original sequence, because the original sequence was only up to this. Okay. The other values on this side were 0. Now, we take some basic elements used for signal processing operations. One is an adder. You have a sequence x1 n, x2 n, the output is x1 n plus x2 n. Okay. Then we have a multiplier x1 n, a symbol for a multiplier is like this, it is a multiplier k. So, output y n gets multiplied by a scalar k, k times x n. Okay. So, this is a multiplier. Then we have the most important element, that is a delay element. If this is x n, if this is a unit delay, one sampling time delay, then y n, the output will be x n minus 1. Okay. If it is a unit delay, the symbol for a unit delay used in different books are, sometimes it is written as capital T, that is one sampling time, sometimes capital D, that is a delay, standard one delay. Mathematicians, they use backward shift operator B, and in the transform domain we also use in textbooks z to the power minus 1, okay, in terms of z transform operator. It is similar to using in a derivative circuit. In many books they write d dt. If you have f t here, you get f dash t here in analog domain. Okay. In the control books, they replace it by s, and mathematicians you will find they write as P DDT operator. In some books they write Heaviside operator capital D. They are one and the same thing, only thing in different domains you use different symbols. If you are working in the time domain only, then you write d by dt, but the moment you use this as a Laplace operator S, then you should not write f t, this is not correct. You should write its transform f s and corresponding output whatever it is. Suppose this was y t, then I will call it y s and not y t. Y s, it happens to be s times f s in this case. Okay. So, the symbol use of the symbol is depending on what domain you are using. In the frequency domain, similarly this will be, if I write f j omega and this is y j omega, then this will be straight away j omega. Okay. S replaced by j omega in the continuous domain. However, in the discrete domain, this is very commonly used symbol, though technically it should be used only when you are using the variables in the z domain. If I am using x z, then this has a meaning, y z will be z inverse of x z. I should not write x n, this is in the time domain, then I should use either b or capital T. Okay. So, b means backward shift operation, that will give me x n minus 1, which is y n. Okay. But anyway, most of the textbooks you will find they use z inverse even in the time domain. Okay. So, this is a common slip, but conventionally it is acceptable. So, we will also use z inverse as an element if required. So, all these symbols will be used sometime or other, they are one and the same thing. So, if you have two delay elements, if I show two delay elements and if this is x n, then what will be the output? X n minus 2. Okay. Next you have another kind of multiplication, that is x 1 n gets multiplied by x 2 n. So, y n output is x 1 n multiplied by x 2 n. This is a modulator. Okay. You must have studied amplitude modulation, frequency modulation, all right. This is also used in windowing operation. That means a function x 1 n, we pass through a window function x 2 n, where the function values will be multiplied by, it will be scaled by different amount depending on the values of x 2 n. Okay. So, basically what you are trying to prune x 1 n by different amounts at different instant. Okay. And that pruning function is x 2 n, that is windowing. So, what is this backward shift operation therefore on x n? X n is a sequence, I can write x n, sometimes we also use x n, all right. So, b on x n will give me x n minus 1. Okay. So, what is x n minus x n minus 1? Will be 1 minus b times x n. So, this we call as differencing operation on x n. So, on x n, if I apply a differencing operator, I get the difference between x n and x n minus 1. It is very similar to your derivative operation. If I have b x n as x n minus 1, what will be a forward shift operation? Forward shift will be b inverse x n, which will be x n plus 1. Okay. What is this shift really meaning? Suppose we have a sequence x n, this is say x 0, x 1, x 2, rest are all 0. This is a sequence, x 0 may be 5, 4, 3. If I give it a shift b of, this represents the general x n, b of x n will give me, this whole thing gets shifted to the right. Shifted to the right means first instant it will be a 0, then only this x 0 will appear, then x 1, then x 2 and then 0. So, it will start with a 0. If I give 2 shifts, then 0 0, then x 0, x 1, x 2. So, b of x n will be shifting the sequence such that these will be the values now 0, x 1, x 2, x 0, x 1, x 2. There is another operator, a summator or an accumulator. Accumulator is the proper name. So, what you get is summation of x n, all right, that is x 0, it is similar to your integration, summation of the sequence up to that point n. What kind of output you get if I excite the system with a delta function? It is delta n is this one, okay, this is delta n, rest are all 0. Now, in an accumulator what will be the output? At this instant it is 1, next instant also it is 1, 1 plus 0, 1 plus 0 plus 0 and so on. So, the output will be u n, okay. It is similar to integration. If I now use it across a differencing operator, what do you get? Delta n minus delta n minus 1, is it not? What will it look like? Okay. This is delta n 1 and minus 1. If I use a delta n the delta function and then an accumulator. What will be the output? So, this one is delta n minus delta n minus 1 and a summation delta n will give me u n and this will give me u n minus 1. So, this will be u n minus 1 which is nothing but again delta function, alright. This is delta n minus delta n minus 1. So, delta n is coming back at the output. So, one is the inverse of the other, alright. So, accumulator is the inverse of a differentiator or differencing operator, okay. So, delta sigma, if we use these notations, is equal to unity, alright, and delta was 1 minus b, therefore, sigma will be do you agree? Can you prove it? Can you prove it? Let us see. What is sigma? It is 1 plus, see sigma, this operator operating on x n, sigma operating on x n gave me x n plus is it not all the values, previous values. So, this is 1 plus this is b plus b squared, an infinite sequence, and this is a GP series. You can write this as 1 by 1 minus b, okay. Now, let us use these elements, let us see how these elements can be used to represent a difference equation, a general equation. Suppose we have a difference equation in this form. We will discuss later on how such equations can be obtained. Okay. Suppose we have an equation y n plus b 1 y n minus 1 plus b 2 y n minus 2 is equal to a 0 x n, a 1 x n minus 1 plus a 2 x n minus 2. One may write where y is the output and x is the input. Okay. So, you can write y n is equal to a 0 x n plus a 1 x n minus 1 plus a 2 x n minus 2 minus b 1 y n minus 1 minus b 2 y n minus 2. Do you all agree? So, from there you can see a 0 x n, suppose x n is the input, then that gets multiplied by a constant a 0 added with a 1 times one delayed function. So, I take x n here, I tap it here put a delay element, you can write B or capital D, then multiplied by A1, then again take another delay multiplied by A2. Okay. So, this is A2 times x n minus 2 plus A1 times x n minus 1. So, they are added together and then finally added with A0 times x n. This is, suppose this is the output y n. Then I am yet to add these two terms. So, that y n from the output side, again I can have a delay B1, then B2, I can add them together and then they are to be negated. Okay. So, these two, from these two feedback channels, the added signals will be giving you y n. Okay. So, there is a multiplier, adder, delay. There are some more special functions, operators we use for changing the sampling rate, all right. One is a compressor or downsampler, and the other one is upsampler or expander. Okay. When we compress it, suppose, okay, let me take the signal here. There is a signal here. This is the continuous domain signal x t. You are sampling at very close intervals. If you have very close intervals of sampling, then you are almost recovering the continuous domain function, okay, depending on the degree of that sampling rate. Now, if you are very close and if you are using sample and hold elements, that means you are approximating this function by this type of function, okay, constant, piecewise constant functions, and if they are very close, then that error will be minimal. Now, suppose the function is changing very slowly, all right, then you can relax the sampling rate, you can reduce the sampling rate. So, you drop, say we take only alternate values, whatever it be those, in between these values I made zeros. Will it be same? If the function was changing very slowly, and if I sample it instead of at this high rate, I have got these sampled values. Now I drop in between these values, we drop, that means we make them zeros, okay. Then we get samples like this that may represent the original signal to a satisfactory level. We could have dropped every third, or sorry, we could have dropped 2 consecutive values, that is we could have taken only the only every third value, x0, then x3, then x6 and so on, and make x1 x2 as zeros. We could have done that, and then you compress it, back to its original sampling time. Then you get the same wave seen in a very compressed form. Okay. You may not lose much of information if the sampling rate, original sampling rate was very high, or compared to the sampling rate the signal is changing very slowly. Okay. So, you can keep on trying to decimate, to downsample, keep on doing it till you find that important informations are getting lost. Till that time you can do this. We will get back to this problem later on. What are the conditions for fixing the sampling rate for a given signal, that we shall discuss in subsequent discussions. So, basically in downsampling we drop the values, these are dropped and then again these are compressed. In upsampling we insert some artificial values, zeros. So, you are given a sequence, say for example you may be given the power demand of our campus at regular intervals of 1 hour, we have the records at say 6 o'clock, 7 o'clock, 8 o'clock in the morning, 9 and so on. I have these values. The demand in megawatt may be like this. One may insert some 0 values inside, because they are not defined, you can insert zeros also. Will it be same? Basically this denotes the profile of the actual variable to a certain extent, all right, because the demand is not varying very fast. So, we can sample it at an interval of 1 hour. Now, if somebody puts zeros here, though initially we said that here it is not defined, but it cannot be 0, is not. Now, if I try to make a 0 here and then the profile will be like this. Is it not? It is not same as this, you are bringing it down to 0. So, there is a sharp change taking place which is not representing the original sequence. A sharp change means high frequency components. So, you have to eliminate this. So, if this sequence is passed through a low pass filter, then you can get back more or less the original sequence. One may insert some values by linearly interpolating these, that is take the values in between 6 o'clock and 7 o'clock, whatever values you want. At 6:30 it will be the average of the data that you get at these hours, all right, this plus this by 2, this plus this by 2, this is a simple linear interpolation of second order. Okay. Then probably it will represent to a certain extent the original profile. Okay. So, for a compressor y n, if this is the output of a compressor, this is x n, and we are downsampling by m, it is x n m. Okay, and rest of the values are all 0. Only the mth value is counted. Okay. Suppose m is equal to 5, then n you put as 1, it will be 1 into 5. So, x 5 will be treated as y 1, x 0 as y 0, x 5 as y 1, x 10 as y 2, and so on. So, this is for a downsampler. In case of an upsampler, y n will be x n by L, where symbol is x n is the input, this is a symbol for the upsampler, that is you are increasing the sampling rate, and y n x is equal to n by L, where n is equal to 0 plus minus L plus minus 2L and so on, and is equal to 0 otherwise. That means, if this is your x 0, x 1, x 2 and so on, okay, then you are inserting zeros here. And you are generating a new sequence. So, x 1 whatever was x 10 sorry x 1 will be now say x 3 or x 4, depending on the number of zeros that you are inserting, that is the factor L. Okay. We will stop here today. Next time we will take up from this point. Okay, thank you very much.